Hello, this is the lecture for section 1.2, domain and range. The domain of any function is the set of all input values to a function, and the range of any function is a set of all output values of a function, right? Usually the domain of the function is referring to x values. And usually the range or the output of the function is y values. The domain, the x's, those are the independent values. The range or the y's are the dependent values, or those values that are determined by the input. They're dependent, the value is dependent on the input, independent variable. All right, when we identify the domain and range of a function, we typically will use interval notation. So let's take a minute and just review how we would write inequalities and interval notation. So, for example, if we had the inequality x is less than -2, in interval notation, we would say that the lowest value in the interval that satisfies this inequality would be -infinity. The largest value would be -2. And we would enclose these values with parentheses. The parenthesis indicates that we want all the values in between these two endpoints, but not including the actual endpoint itself. We can't include -infinity, of course, because it's a concept. We can never reach -infinity. And here, because it's x is not less than or equal to -2, but only less than -2, we must exclude the actual value of -2. Right? So if we were to graph this interval or this inequality on a number line, it would look like this. If -2 was, say, right there, we would be interested in all the values for x that are less than -2. So everything to the left of -2, open-ended, put an arrow there to indicate it goes on forever and ever. But we would use an open circle here by the -2 to indicate we want all the values, excuse me, as close as we can get to -2 from the left, from the small sign, but we don't want to include the actual value of -2. Okay, contrast that with this next example, x is greater than or equal to -2. Here we also have an open-ended inequality. In this case, though, it's open-ended the other way, right? The values that x can take on are greater than or equal to -2. So it'd be everything to the right of -2, like that, okay? So we would write that interval, all these values between -2 and infinity, as -2 to infinity. Of course, we always have a parenthesis next to infinity because we can never reach it. But because we have this or equal to under here, we can include that actual value of -2, right? So if we were graphing it, we would put a filled in circle there to indicate it does include the endpoint, the -2. And when we write that in interval notation, we would use a square bracket to indicate the interval is inclusive of that endpoint next to the bracket, right? And then we just have some other examples of how we might write different intervals for inequalities. If x is between two values, we have the lower bound and the upper bound. Of course, if it's not or equal to, we want to use a parenthesis to say exclude that endpoint. If it is or equal to, we want to use a square bracket. We want to use a square bracket to say that we do include the endpoint. Okay. This chart also has set builder notation on it. We don't use this very often, but if we did, basically what we're saying here is we have these curly brackets that surround it. That's indicating that what's inside there is a set. And this would read the set of all x values such that x is less than -2. Right? So that's in set builder notation. It's a way of writing the inequality x is less than -2. In interval notation, we would say -infinity to 2. Okay? Different ways of expressing the same thing. And this is typically how we would describe a domain or a range of a function. Right? if the domain or range is all real numbers, we of course would just say negative infinity to positive infinity in interval notation. In interval notation. In set builder notation, we would just say the set of all x such that x is an element of, and this funny looking R, usually it's a double stemmed R, is a symbol that we use to say all real numbers. So the set of all x such that x is an element of the real numbers. Okay, that's what that weird rounded out E symbol means. Okay, let's see if we can look at a few more examples here. Maybe practice writing inequalities in different notations, and maybe actually finding the inequality from an interval notation. Look at the first line. This might be kind of hard to see. There's an inequality there. It says x is less than 6. There's an inequality that says x is less than 6. So this is indicating that I'm interested in all the values that are less than 6. If I were to write that in set builder notation, I would use a curly bracket, and I would say the variable is going to be x. So this would be the set of all x, and the vertical line means such that. So it would be the set of all x such that x is less than 6. And then I'd use that curly bracket that indicates that's the end of the set. Okay. In interval notation, of course, I just want to identify the endpoints. Well, it's open-ended to the left, right? X is less than 6. Right? If I'm graphing that, let's say 6 is right here. X is less than 6, so it's to the left of 6. It's not equal to 6. There's no or equal to, so I'd have open circle there, right? So in interval notation, then I'd have to write that my lower boundary is simply negative infinity. My upper boundary is going to be 6, and I want to use a parenthesis because I'm not saying less than or equal to here. It just says less than. So I do need to exclude that boundary of 6, that actual value of 6. 5.99999 is in that interval, but 6 itself is not included in the interval. Right. The next line, all we have is set builder notation. It says the set of all x such that x is less than or equal to 7 or x is greater than 13. Okay. Well, in inequality, I've got two inequalities going on. So that's going to be, the first one is x is less than or equal to 7. The second inequality is x is greater than 13. Okay, to write that in interval notation, I'm just going to have to write two intervals. Okay, that first interval is everything less than or equal to 7, right? So how does that look on the number line? If 7 is here, less than or equal to 7, that'd be a closed circle here. Everything's smaller than 7. That's going to be negative infinity to 7, right? That's the first interval. And since it's or equal to 7, I'll use the bracket here to indicate a closed interval there. Now, or the second interval is going to be x is greater than 13, right? So if 13 is out here somewhere, it'd go off to the right. So my lower boundary here is going to be 13. My upper boundary is simply infinity. And it's not or equal to 13, so I'll put a parenthesis by my 13. Now, when I have two intervals, or two inequalities here that I'm writing in interval notation, these are actually sets of continuous, they're continuous sets, right? So it's a set. I could never list all the elements of that set because it's an infinite number when I include all the decimals, but they are still sets, so I would join them together with the union symbol. It's kind of like a U like that, okay? Here I have an inequality, 0 is less than x is less than or equal to 1. Well, in set builder, it's not that difficult. I just say the set of all x such that 0 is less than x is less than or equal to 1. Okay, there's set builder. Now the interval, here it's telling me the value x can take on is in between 0 and 1. So my two boundaries, or my two endpoints here, are 0 and 1. 0 has to be less than x, not less than or equal to. There's no line under that. So the parenthesis by the 0, but x can be less than or equal to 1, so I would want to put a bracket by the 1. Okay. Look at this interval here, -8 to -5, inclusive of the -5, that's a square bracket, but not inclusive of the -8. right? That's a parenthesis. So what would that inequality be? Well, my value is going to be in between -8 and 5, right? So it'd be -8, -8 and -5. So -8x, -5. And let's see, since there's a parenthesis by the -8, -8 is just going to be less than x. But I've got the bracket next to the -5, so that means x is less than or equal to -5. And of course, set builders, no rocket science. Set of all x such that, such that -8 less than x less than or equal to -5. Okay. Now look at these next two. There's two intervals, right? That means there's going to be two inequalities, right? So let's see. First, I have the interval from -infinity to 3. Well, that means that x is less than 3, but I got that square bracket by the 3, okay? So it's less than or equal to 3. Got a line under there. And then the other one, or it's 4 to infinity. So that's going to be x is greater than 4, but I have a parenthesis by my 4 here, so I don't want the symbol to be or equal to. I just want x is greater than 4, not x is greater than or equal to 4. Okay, and that's that builder. And then this last one, I guess I'll write that symbol x such that x is less than or equal to 3, or x greater than 4. This last one here is kind of interesting, though. This last one, there are two intervals, -infinity to 2 in union with 2 to infinity. All right, so what is that saying? There's two intervals. You'd think I would do something like this, right? But because the only thing being excluded here is just the actual value of 2, I parentheses by my 2, it's probably easier to simply say x cannot equal 2, right? Set of all x such that x does not equal 2. Okay, it'd be kind of weird to say such that x is less than 2 or x is greater than 2. It's just easier to say x is not equal to 2. All right? So inequality notation is how we identify intervals for inequalities, and that's how we describe the domain and the range of a function. Right? So let's look at some examples, and let's see if we can identify the domain and the range. Okay, so here we have two graphs. Let's look at the one on the left first. Kind of hard to see, so let me trace over it. One part of the graph looks like this, and I'll stick an arrow right there. And there's an open circle here. And the other part of the graph has a closed dot there. It comes up like this. And then we'll just put an arrow on there as well. It's hard to see these numbers, 0, 1, 2, 3, 4, 5, 6, 7, so on. 1, of course, is up there, -1, -2. So there's our graph. Now, if I want to identify the domain of this graph, let's see, I guess I'll put it right here. Domain, recall, those are all your x values, right? All your inputs to the function. And when we're graphing in the Cartesian plane, the inputs or the independent variables are going to be our horizontals or our axes in most cases. Okay, so what we want to do to identify this domain is we want to just say what is the interval of x values that have points on the graph. So let me say that differently. What is the interval of x coordinates of any point that's on this graph? Right? Well, if we look at the left side of this graph, this arrow is indicating it goes down and to the left forever and ever. So x values are left, right. Clearly, the smallest x we can ever have is -infinity. Okay, well, what's the largest x? When we go up here, as we move right across the graph, we can see there's a little gap here. As we move right, we can see that that graph, it stops right here at 3. So, and then it starts up again at 4. So I'm going to have to close this first interval at 3. Since it's an open circle there, that means I don't include that endpoint. I need a parenthesis by it. It's going to start up again. So the first interval is -infinity 3. The second interval is going to start up at 4 with a closed circle there indicating a square bracket. We want to include that endpoint. But then that arrow indicates that it goes up and to the right forever, so my upper bound is going to be infinity. Okay, I have two intervals, which are two continuous sets, so I want to join them with the union symbol. Here's our domain. Now the range, recall, is all the possible outputs of a function, and in a graph, that's going to be the y's. Okay, the range is going to be the y's. So I want to find the smallest y to the largest y to identify the range. Well, the smallest y, since this off to the left here, this arrow is going down forever and ever, the smallest y is going to be negative infinity. What's the largest y? Well, I do have this break in the graph here, but when I'm looking at y coordinates of points, right, or when I'm looking at the graph as it moves from low to high values of y, the break occurs right here at y equals 0. But look at that. There is no gap in the range because on the first part of the graph, y equals 0 is not included. We've got this open circle, right? The coordinates of the point where the open circle are, those coordinates are 3, 0. 0 is there, and so it couldn't be included. So I'm tempted to write 0 and close off that interval and start it again, except look, the second part of this graph starts at y equals 0. Look, the coordinates of this point here are 4, 0. Okay, so it starts at 0. So I don't really need to stop and start, even though it's a different part of the graph. There's no break in possible y's, so I can keep on going, and then it goes up to infinity. So my domain here is going to be negative infinity to 3 in union with 4 to infinity, because I do have this break in the graph that is affected horizontally by x values. There's this period or this interval in between 3 and 4 that doesn't have any graph to it. There's no graph there, so that needs to be excluded from the domain. But the range has no breaks. It's just negative infinity to positive infinity because, you know, as we move from a low down to up on the graph, or low y values to high y values, there is no break in the y. The one place where there could be a break, it's covered by the second portion of the graph. Right? If we look at the second example over here, let's retrace that. That has an open circle on that end, and this is a closed circle here, and then we can see that the graph is a parabola. It's a parabola that's just sitting right here on the origin. Okay, one is here, let's level that a little bit. So there's our y-axis and our x-axis here. So the domain here are all our possible x values is what? Let's see. We're going to go left to right with our x, right? The smallest x is here at -2, but I've got the open circle. So I want to say parenthesis -2, comma, to indicate this interval is continuing. We're all the way up until the furthest right portion on this graph is occurring right here at x equals 2. So the domain is -2 to 2, and since I have that closed circle by the 2, I want a square bracket indicating that the value of +2 should be included in the interval. The open circle over here by the -2 is saying don't include -2 in that interval. So parenthesis by the -2, square bracket by the +2. Okay, range, our y's. Range again is smallest y to largest y. By the way, intervals must always be identified from smallest value to largest value. So range was my smallest y. Looks like it's right here at 0. That's the lowest point on that graph. And should I include that point in the interval? Well, yeah, that point with the coordinates 0, 0 is on the graph. So I'll put a square bracket there to indicate that I want to include that point of 0. What's the highest y? Comes up here right at y equals 4. It's not included on the left side. The 4 should be included by the closed circle on the right side. That's going to override the don't include. So I'm going to go ahead and put a square bracket by that. So there's my range 0 to 4 enclosed in square brackets. All right. We can also find the domain and the range of a function from an equation or from an algebraic representation, the formula, if you will, for a function. Okay. The easiest way to think about finding the domain from its algebraic representation is to start by assuming all real numbers. That's our initial assumption, all real numbers. Okay, and then we just inspect the formula or inspect the equation to see if we need to remove any values from the domain, to see if there are any excluded values, if you will. Okay, if we have a rational expression in there, a fraction, right? If we have something where there is a variable in the denominator, all right, there's a possibility that we can have a zero denominator. And can we ever divide by zero? No, that can't happen, right? So we have to find any values that might result in a zero denominator and remove those values from the domain. They would become excluded values. Okay, if our function, our equation has a negative, or I'm sorry, if our equation has any even radicals, right, like a square root or a fourth root or a sixth root, okay, we can't have a negative value as the radicand, the part that is under the radical, because functions limit themselves to real numbers. And if there's a negative radicand, like say the square root of -4, what is the square root of -4? I can't determine what that is without introducing an imaginary number. We don't do that with functions. So if there are any radicals of an even root, like square root or fourth root, I have to make sure that any values that make a negative radicand are removed. They would also be excluded values. Okay. And then lastly, if my function is a logarithm, if it has a log in it, the arguments of logarithms have to be positive. So if there's any non-positive values in the argument, I would have to remove those as well. All right. So there are three things to think about with domain, finding the domain from the algebraic or the formula of the function. Those three things those are the three exceptions I need to think about. If none of those three things exist, then my domain is going to be all real numbers. All right, let's look at some examples. Look at this first example here, f of x. If I was to find the domain of this function, I'd want to think, does it address any of those three exceptions? Well, is there a denominator? Yeah, and it has a variable in it. Okay, so there's one exception. Any even roots? There's no radicals. Any logarithms? No. So I only have to deal with that one exception. I have to make sure the denominator does not equal 0. All right, so the easiest thing to do is just to take that denominator, 3x plus 4, say it can't equal 0, and then solve for x. Right? So I'll subtract the 4. So then 3x can't equal -4, and then divide, both sides by 3. So I find that x cannot equal -4/3. That's the only value that we have to exclude from the domain. Right? So if x cannot equal -4/3, my domain then is going to be -infinity all the way up to -4/3, but parenthesis by it to indicate exclude that actual value of 4/3, right? And then join that in union with, we'll start back up again right after -4/3 and go all the way to infinity, right? If I were to draw this on the number line, it would look like this. Let's see, if 4/3 was right here, I'm sorry, negative. If -4/3 was right here, this interval on the number line would have the open circle at -4/3, but everything to the right would be good, and everything to the left would be good. Okay? Excuse me there. The next one here, g of x, now that says the square root of 9x minus 3. The square root of 9x minus 3. Well, I don't have any denominators here or logs, but I do have a radicand of an even root. It's a square root, right? Invisible to there, right? Square root. So what I have to do here is I have to say, well, the 9x minus 3 can't be negative. So that means it has to be greater than or equal to 0. It has to be greater than or equal to 0. And let's solve for x. So add the 3. Then 9x has to be greater than or equal to 3. Divide by 9. So then x has to be greater than or equal to 3/9, which of course reduces to 1/3. Right? So on the number line, what is that going to do? Let's see. If 1/3 is here. We want everything greater than 1/3 and including that end value, so that's a closed circle. So my interval for my domain is going to look like this. It's going to be square bracket 1/3 all the way to infinity. Okay, now this last example, well, this one's kind of interesting. I don't see a logarithm there. I don't see a logarithm, but h of x is equal to x divided by the square root of x plus 2. So I have both exceptions being addressed in the same formula here, right? The same equation. So let's see. Well, I got to address both situations then. I need to say that, first of all, the square root of x plus 2 can't equal 0, because if it did, right, if it did, that would be dividing by 0. That's not allowed. Okay, but I also have to say that the square root of x plus 2, I'm sorry, not the square root, just the radicand, x plus 2 has to be greater than or equal to 0, because even roots have to have positive or non-negative radicands, right? Well, these two sort of contradict each other. I need to take the most restrictive result here, because these both have to be addressed, right? So since the square root of x plus 2 cannot equal 0, if I'm solving for x, let's see, I'll just square both sides. So x plus 2 can't equal 0 squared. Let's do 0 and subtract the 2. X cannot equal -2. Okay, there's one restriction, but there's more. X plus 2 greater than or equal to 0. Well, if I subtract the 2, this side over here is saying, right there, that x has to be greater than or equal to -2. Well, since it can't equal -2, it's got to come out. Really, the only thing that can happen here is x has to be greater than -2, since this other restriction applies as well. All right, so writing that as an interval, my domain here is then going to be -2 to infinity, but we have to exclude that -2. It can't be equal to -2, just greater than. So I want a parenthesis there. All right. All right, the last topic in section 1.2 is piecewise functions, or piecewise defined functions. I think that's kind of hard to see, isn't it? Something's happening with my focus. So I don't get it to. Anyway, I'll read this to you. It says a piecewise function is a function in which the formula used depends on the interval of the domain that the input is in. The input lies in. The notation of piecewise function looks like this. F of x equals formula 1, maybe x is greater than 2 or something, if, and then we give an interval of the domain to which this formula applies. F of x equals formula 2 if we give a second interval of the domain. Maybe there's a third formula and a third interval, a fourth formula and a fourth interval, so on. So let's take a look at an example of writing a piecewise function. Okay, this says a movie theater charges $5 per person for a special movie showing for groups of 1 to 8 people, or a fixed fee of $42 for a group of 9 or more. And we need to write a function that relates the number of people, n, to the total cost of the movie. All right, so I think that the easiest thing to do here is to start with the writing the formulas, if you will. Okay, so it looks like what's our domain and our range going to be here? Well, the input, or the independent variable that determines the dependent variable. The independent variable is going to be how many people are attending, right? How many people are attending, because the cost is dependent on how many people attend, right? So the domain is going to refer to how many people are attending. The range, or the outputs, would then be the costs. Okay, so there's two things going on here. The first thing, maybe we'll call this function c of x, right? Yeah, where we can say X is the number of people. Oh no, they want us to do something else. There it is, N. N is going to be the number of people attending. Okay, so C of N, right, or the cost given the number of people attending is going to equal, in this case, we're going to have two different rules, right? The first rule says it's $5 per person for groups of 1 to 8. So $5 per person, that would be 5N, right? 5 times the number of people attending N, but that's only if N is between 1 and 8. So we'd say 1 is less than or equal to N is less than or equal to 8, right? Now, the second part says that it's just going to be a fixed fee of $42, just plain old 42, if there's anybody, if there's 9 or more people, right? So C of N is going to be 42 if N is greater than or equal to 9. So there's my two values there. All right, so let's see. If I wanted to graph that, how would I do that? Let's see, graphing that. Well, let's see. It's hard to see, but here's my x-axis and my y-axis, or in this case, it's my n-axis and my C of n axis. It's going to be 5n for n equals 1 to 8. So 1, 2, 3, 4, 5, 6, 7, there's 8. Okay, so 5n, 5 times 0, well, that's 0, right? There's 0. The vertical grid here is in terms of 5, so that's 5, 10, 15, 20, 25, 30, 35, and 40. Okay, so 5 times 1 is 5, 5 times 2 is 10, so on and so forth. So this increase. Each time the person increased, the cost increased by $5 all the way up until 8 people are attending. Okay, so there's the first part of the graph. But after 8 people, we have a fixed price of only $42. Actually, there's nothing between 8 and 9, so we can't have a piece of a person, right? So if 42, we'll say, is right there, the rest of this graph then is going to have to do something like this until we reach theater capacity, whatever that is. This must be a straight line. Okay. Let's look at one more example here before we close the lecture. Here we have a function, f of x equals, it's a piecewise function. There are 3 pieces to this function. The 3 rules are that f is going to equal negative 2x if x is less than negative 2. It's going to, the rule is going to be x plus 4, or add 4 to the input, if the input is between negative 2 and 2, inclusive of the negative 2, right? Or negative 2 is less than or equal to x is less than 2. And then f of x is just going to be 6, the constant function, if x is greater than or equal to 2. Okay, so I have 3 intervals of the domain, right? If I want to evaluate f of negative 5, let's see, which rule should I use when x is negative 5? Well, if I go up here and look, let's see, x is less than negative 2, negative 5 is less than negative 2, so I want to use the first rule, right? So f of negative 5 is going to be negative 2 times negative 5, right? Or 10. Okay, evaluate f of negative 2. Well, where is x negative 2? Which interval? Well, in the first interval, x is less than negative 2. In the second interval, negative 2 is less than or equal to x, which is less than 2. So I want to use that second rule because that's the interval that my value of x falls in. So when x is negative 2, f of x is going to be x plus 4, or negative 2 plus 4, which of course is 2. All right. What about f of 0? Well, f of 0, it fits in that second interval, right? So that's just going to be 0 plus 4, or 4, right? How about f of 2? Does that still fit in that second interval? No. X has to be less than 2. We have to move down to the third interval where x is greater than or equal to 2. That means f of 2 is simply going to be 6. f of 3, well, that's also going to be 6 because when x is 3, it's still greater than 2, and it's going to be a constant function. All right. If we're going to graph this function, here's my x and my y axis. Let's see, I've got some intervals. -2 and 2 seem to be my boundaries. Let's see, -1 is there, -2 is there, 0, 1, 2, there's more. Just label a few things. Okay, there's some y's, 1, 2, 3, 4, 5, 6, and so on. There's -1 and -2 down there. All right, well, let's see. -2x. So if x is less than or -2, that means f of x or y. So remember, f of x, that's function notation for y. Y is going to be -2x. All right, well, let's just see what happens when x is -3, for example. When x is -3, -2 times -3, that's a +6. So y will be up here at 6. How about -4? -2 times -4 is +8. So that'd be up there. Okay. What about when x is actually -2? When x is actually -2, the second interval applies. But this first interval doesn't stop right up until it gets right up to -2. Okay. So what would happen if we could have -2 in that interval? Well, the y would be -2 times -2 or +4. It can't be that, but it can be everything close to that. So I'm going to put an open circle at 4 to indicate that every value close to 4 is good, but not 4 itself, right? So this portion of the graph then is going to look like this. And it's going to keep going, so I'll stick an arrow because it's an open-ended interval, right? Now the second part is x plus 4. Now this applies to values in between -2 and 2, but inclusive of that -2. Well, let's see what happens right at -2. Well, -2 plus 4 is +2, right? So that means the first point for the second interval is right here. And since -2 is less than or equal to, that's going to be a filled in dot at that end value, right? 0 is in there too. Well, what is 0 plus 4? That's 4. All right, so that point would be in there. What about -1? -1 plus 4, that's 3. 1 is in there. 1 plus 4, that's 5. 2, all right, 2 itself is not there, but everything close to 2 is, right? So 2 plus 4 is 6. So I'm going to put an open circle at 6 to indicate everything close to it can be in there, but not the actual point that has the x coordinate of 2 on it, right? So there's my second interval. My first interval is this line, second interval is this line. My third interval is just a constant function. When x is greater than or equal to 2, y is simply 6, right? So let's see, when x is 3, y is 6. When x is 4, y is 6, so on and so forth. It goes forever. What's the lower boundary here? It's 2. Well, when x is 2, y is 6, the lower boundary is right here at the upper boundary of the middle interval. That happens sometimes. But since they share that same point, I'm going to go ahead and fill in that dot there because, actually I don't even really need that dot there because the two intervals meet each other. Okay, so that point right there with the coordinates of 2, 6 is on the graph, but it's in the third interval, not the first one. All right, so that closes the lecture for section 1.2.